In this lecture, we discuss some of the requirements that are very important to understand for developers of device drivers. An introduction will be given to requirements of the variety of available I/O devices, requirements under which these I/O devices work, some operational parameters of these I/O devices, and some of the timing issues that are central to understanding device drivers. So, in most of the courses of computer science, all the focus is put on the CPU and memory, and how does that works, and that is central to understanding subjects like computer architecture, computer organization and assembly, operating system, data structures, algorithm analysis, etc. However, a computer with only a CPU and memory is kind of a very boring system, right? It is only the IOs that makes the computer interesting. Without IOs, computers are useless and like disembodied brains. You have got a lot of computers, devices, lots of phones, lots of memory devices. Here is where the operating system really helps in providing a standardized interface to these devices, so that the programmers doesn't has to care about whether he is storing data to a floppy, a hard drive, a USB drive, or getting data from the network. The user really doesn't care about these things. So how can we standardize these interfaces that are different to each other? Another thing that the operating system deals with is that these devices are fundamentally unreliable. Media failures and transmission errors could occur. So it is important that the operating system should make them reliable. Another thing that is interesting is that these devices are unpredictable or slow. So the operating system will also have to be responsible to manage that as well. So how can we manage them if we don't understand their functionality? Let's go further to discuss some of the parameters that govern the working of these devices and try to work for a standard interface that would abstract away the requirements of different devices. Having talked about some of the requirements, let's talk about some operational parameters of this problem. As we said, that there is a whole spectrum of devices that work under various operational parameters. Here are a few of those problems. We have devices that operate based on transferring or receiving data in bytes or blocks. So is a disk drive a block device or a byte device? A block device. Why? Because it deals with blocks, virtual pages. And in contrast, a mouse is a byte device because it sends one byte at a time. The Ethernet, on the other hand, is a block device because it sends packets of data comprising of whole blocks of information depending on the protocol used. How about a USB flash storage device? Well, there are USBs that are block devices as well as few that are byte devices. Then you might ask whether the access is random or sequential. Or in other words, do you have to get things in order or you might get them completely in a random order? The tape drives are example of sequential interface, while the disk drives, CD drives, and network devices are examples of random accesses. For example, network devices send data using various protocols. However, the data can take any path that might be longer or shorter than others. So the network receives these packets of data randomly and has to put them in order before any use. Another question that is of quite importance is that are you accessing these devices through polling or through interrupts? Do you wait for the device or you have to interrupt whenever the device is ready? As we said that there are many things attached to the computers. So here we can see a whole spectrum of devices that needs to be dealt with at the same time. There is a central bus, uh, through which you connect these devices. You probably got a bridge controller, PCI bus, SCSI buses, expansion buses, IDE buses for disk drives. Then you might have a network stuff, right? When you look at the real system, as can be seen on the screen, this CPU and memory kind of thing is small pieces, and the rest is what makes the entire world. So we get everything from the keyboards that have very slow transfer rates to buses that are running at gigabits. So the operating system needs a mechanism that is able to handle this wide range of devices. The system has to minimize the overhead byte for fast devices and should not waste time waiting for slower devices, right? So the system better be able to handle this wide range. Better not have high overhead for fast devices. Better not waste time waiting for slower devices. So what's the goal of the I/O system? It is simply to provide a uniform interface, despite the broad spectrum of devices that have different requirements. Here is an interesting thing. Here is an interesting code. We do a file open on dev something, and we write, we go through it, and we fprint a bunch of stuff to it, and then we close. Notice that that other than maybe what the word something is, we don't know anything about the device. This is the standardized piece of code that works on a variety of devices. Why does it work on a variety of devices? Because the device drivers provide a standard interface. That's one of the goals. It doesn't matter whether it's a USB drive or it's a disk drive or it's a network device. That's what the device drivers really do, that implements a standard interface. We also need to learn about the standard interfaces that exist among the available devices in the market. So mostly there are three device interfaces in modern computer systems: block devices, character devices, and network devices. So we'll start with the block devices. Block devices are things that access in blocks. So like disk drives, tape drives, DVD ROMs, etc. We use system calls such as open, read, write, seek, etc. To access files, you can also memory map these block devices. So you can take a file and you can map it in memory using mmap. As a result, you end up with a file that takes up a chunk in memory that you can read and write by reading and writing the memory. Then we have the character devices that tend to work in bytes. Keyboard, mice, serial ports, some USB devices works on this principle as well. And typically, these devices send or receive single character at a time when with system commands such as get, put, etc. Usually the libraries are on top that allows line editing. And finally, the network devices. The network devices are things like Ethernet, wireless, and Bluetooth. These devices are different enough from the block and character devices to have their own interface. Mostly the kinds of network devices that you would encounter are accessed using socket interface. Socket is an endpoint communication. You need two sockets, connect them together. You write data in one socket, it comes out the other side. So it is a bidirectional interface, and it is a generic endpoint communication. Their uses are in FIFOs and streams of data, queues and mailboxes, etc. Let's now talk about the timing access of these devices. We have the block interface that tells the processor to wait. When request data, so you go to read or write, and your thread is put to sleep until the data is ready. Similarly, you go to write and your thread is put to sleep until the data arrives and is ready. This is the standard way that we do things since we were born, right? But then again, we have other interfaces. We have other options that are different. We have the non-blocking interface. The system does not wait. You say, well, do whatever you can do immediately for me and tell me how much you did. So the processor says, read 100 bytes. And the device says, I have only 2 bytes. What are the circumstances that only 2 bytes can be returned yet? Because maybe the user hasn't written anything yet, or at the time of request, only 2 bytes were dispatched, and the program has to go to the disk to move the other bytes from the disk. So that's a non-blocking interface. You can get back with some status in terms of how much was actually accomplished. In the case of asynchronous interface, it returns to you immediately with a promise, and later the system will signal you that here are your bytes. So I hope you understand the difference between the non-blocking and the asynchronous interface. So in asynchronous, basically when request data to take the pointer to user's buffer returns immediately. Later the kernel fills the buffer and notifies the user. When sending data, it, it takes the pointer to user's buffer, return immediately. Later kernel notifies the user. I hope you understand the difference between the non-blocking and asynchronous interface, right? So now the asynchronous version actually requires some callbacks. Typically, you register a user level interrupt handler that says, okay, run this function when the data is back. Whereas the non-blocking, I do the read, a system call. It comes back immediately with whatever it could. If you could see this little portion in the orange, this is almost negligible relative to the rest of the blocks in the diagram, right? We could see that the modern system of today is comprised of a whole lot of I/O devices, which is what made it possible for the interesting applications out in the market. So whenever you change the design of the microprocessor, you also change these two chipsets because they are designed for working with a specific family of processors. These chipsets are responsible for communication between the processor and the external devices. The chipset plays a critical role in determining the performance of the system. So we have these two chipsets here, also known as the North Bridge and the South Bridge. But then they also have a more technical name. So the North Bridge is called the Memory Controller Hub, MCH, and the South Bridge is also called I/O Controller Hub, ICH. The North Bridge or the MCH is connected directly to the processor via the front side bus, and it's thus responsible for tasks that require the highest performance, which is why the MCH is connected to fast devices such as the DRAM and the graphics card. On the other hand, the South Bridge or the ICH is not directly connected to the processor. Rather, the North Bridge links the South Bridge to the processor. And the ICH is connected to slower devices such as serial ports, the USB. We got the audio, BIOS interface, and buses for disk access and PCI interface, etc. So what do we mean by slow and fast devices? So we really need a fast interface from the DRAM to the processor and from the graphics card to the DRAM and the processor. And on the other hand, the ICH is connected to devices that have a very slow rate. And one chip can handle them all, right? How does the processor actually talk to these devices? As we know that the processors and memory communicate with each other using a combination of some specialized buses, the address bus, the data bus, and the control bus, right? The CPU would also talk to devices attached to a set of adapters through a central bus and an interrupt controller. Let's consider a device for example, a graphics card. If you look inside this device, The device is talking through a bus adapter to the memory bus and being able to give interrupts to the interrupt controller. There might be some memory inside, and an actual graphics memory usually has a lot of memory for graphics processing. It also has a set of registers that control the device. So by reading and writing, you are putting it in different modes, such as VGA mode or high density graphics mode. You could do that with a bunch of registers. So in short, any device that you are going to look into is going to have a combination of control registers and memory. So the question, how does the processor actually talk or access these devices? Or more precisely, what is the role of a device driver here? So regardless of the complexity of the connections and buses, now we know that the device is controlled by reading or writing the control registers of the device. So the processor accesses registers in two ways. IO instruction, certain processors such as the x86 based processors that have IO instructions. And what an IO instruction is, it is like a load store instruction. But rather than talking to a memory address, you actually talk to the special IO address, the special IO space. And so there is a typical set of ports that are really addresses in IO space. And by executing an in or out instructions, which is like a load or store in this special IO space, you end up reading or writing the control registers on the device. So the device driver needs to know where the control registers are mapped, so it can execute the write in and out instruction in order to do the IO operation. The other option is the memory mapped IO. Memory mapped IO actually takes some of the various parts of the system and maps them into the physical address space, which is also shared by the processor. Think of this as an external extended RAM. You have your regular RAM and extra RAM to accommodate IO devices. Now the processor does not need a special instruction, any special instructions to access IO devices. A load instruction with the address in the range of physical RAM will load from the physical RAM, and a load instruction with an address which falls within the range of range allocated for the IO will load from the IO device. So the processor then just needs to read or write them by mapping them with their base table. Memory mapped IOs are by far the most popular choice implemented in modern computer systems because not all processors have IO instructions. But if you happen to write device drivers, then you will certainly run into these IO instructions. Here is a typical physical address space. The other option is by writing to display memory. That is also called the frame buffer. You could put your individual pixels, essentially changing the image of the screen. Another option is that you might write a set of commands or description in the command queue address space. For example, you might have some triangles and rectangles that makes an interesting scene, and all of a sudden we have an interesting display. Similarly, writing to the command register may cause the onboard graphics hardware to wake up and do something. So you might be thinking that the controller has to go to the main memory to get the information that needs to be displayed on the screen, which would have been very slow, right? In reality, the CPU writes to an address, and that address actually is mapped to the hardware of the device. And that address comes through the memory bus. The bus adapter attached to this bus recognizes the address and goes directly to the device and doesn't ever goes to the memory. So once you have memory map device access, then you can give full control of the device to the user in some process. You just map the physical control parts of that to the user address space, and suddenly there is a piece of virtual memory that they can read and write to cause the device to do something. So under the control of the operating system, it can choose to get full control of the devices to a particular process.